Hello everyone, welcome back to Introduction to Semiconductor Devices. This is lecture 3 of first week of the course. So in the last lecture, we were talking about the 2D visualization model for bonding in silicon. We said that every silicon atom is bonded to 4 different nearest neighbors, which are silicon atoms, and then there is a covalent bond between these atoms. And so you have essentially 8 electrons surrounding each silicon atom. From the original silicon atom and 4 from the neighboring atoms. So that's how we satisfy the valence requirements. And then we have the bonding happening. And because of that, we saw that there are energy bands formed. And we saw two different forms of energy band representation. One is energy bands in space, where we will simply, this could be a position. Okay. And you have the band splitting up into valence band and the conduction band. Okay, this is valence E. All right. So you have the valence band which is completely full, and conduction band which is empty. Right. So all the electrons are occupying the lower band, and there's a band gap Eg. So this is one representation which we will commonly use whenever we draw band diagrams for PN junctions or MOSFETs and so on. And then the other form is what is known as the EK relation. This is essentially the band diagram in the Fourier space. K is the wave vector. So energy versus K diagram, EK diagram we call it. So here it essentially shows you the various states that are available. We saw the dispersion for a free electron. EK diagram for a semiconductor is similar to that. So for a chronic penny model, we just showed you, we didn't solve it, we showed you that EK diagram will look something like this, wherein you have the lower bands and then you have the valence band, which is full. Okay, this is full of electrons. And then the conduction band is one which is right above that, and this is conduction band, and this is empty. So it has lots of states available for electrons to fill up. Okay, and the gap between them is basically Eg. This is simply another representation of it, and this is useful for distinguishing between direct and indirect band gap semiconductors that we will do towards the end of today's lecture. Okay, so that's why we want to look at EK relation, and also it's useful in explaining a few concepts like mobility and things like that. Okay? Other than that, we will use most of the time the energy bands with respect to position. Okay? And there is one more aspect I wanted to just emphasize one more time, which is I'm leaving the figure captions on the slides. Okay, I'm putting the captions deliberately. Whenever you see this, this means that I have taken that particular figure from the appropriate section in the textbook. The textbook basically Semiconductor Physics and Devices by Donald Neiman. Okay, the 4th edition of it I have taken. So if you have any doubts or if you would like to learn more about it, you could go back and look at the textbook. Otherwise, if you're able to follow along with the lecture, that should be sufficient. And by the way, the textbook is actually having a lot more details. Okay, so if you try to read the textbook from beginning to end, I think it will be a lot of material for you for this course. So I'm picking sections from the textbook, and if you are able to follow along with me, that should be sufficient for the purposes of this course. All right, let's get started. So today we would like to talk about electrons and holes in semiconductors. Okay, and this is one of the fundamental concepts in understanding electrons and holes. How they behave is one of the fundamental aspects. All right. So we talked about this 2D bonding model. We said that there are these bonds, and the line represents an electron. What happens if one of the bond breaks? Right? If the bond breaks, that means the electron is simply breaking and going away from the location, physical location of the bond. Right? Then essentially you have this electron which is moving around, and that can go anywhere it wants, unless it is captured by another lattice site. Okay, so whenever this happens, physically this is a picture on the left. You can also represent it in an energy band diagram by showing an electron which is going from the valence band to the conduction band by the arrow. Okay, that means the electron has this particular arrow, this particular transition is telling you that the bond between the electron and the silicon atom has been broken. It requires, of course, some energy, right? You have to supply that energy, otherwise this bond cannot break. So the amount of energy you need to supply is basically Eg. When you do that, it goes into the upper state. Upper state has lot of empty states, right? Conduction band we saw is completely empty. Okay, so then this can happen. Okay. So this process, this is how we represent it, and of course, we find it difficult to draw all these gray shades and all that. So many times we simply represent the band diagrams in the form of these two lines. The upper line EC, this represents EC. This represents the bottom of conduction band, bottom of CB. Similarly, this represents top of VB, valence band. Okay, and between them we have a forbidden gap. That means there are no states available for the electron to be there. All right. So we will adopt this simple line. If you draw a line like this, it implies that there are of course many states available here, and of course there are many states available here. Okay, that is the implication. Okay, which is we take it as a convention from now onwards. All right. So we have created these electrons and holes. Are they able to carry current? Okay. What does it physically mean? Okay, one more time. What does it physically mean that electron is in conduction band? Physically, it means that electron is free to move. Free to move in the lattice. All right. And what does it mean that electron is in the valence band, or hole is in a valence band, right? Well, okay, we will talk about it. Hole in valence band. Hole in valence band. Okay. Okay. So before we do that, can the semiconductor carry current? Okay. Look at it. Let's say first assume that the temperature is 0 degrees Kelvin. Okay. Can this semiconductor carry current? If you look at it, right, you might be inclined to say yes, because you have so many electrons available, right? Each silicon atom has 4 electrons, and then there are 10 power 22 silicon atoms per centimeter cube, right? So you have a huge number of electrons, and if you have so many electrons, why can't it carry current? Of course it can, right? But then it turns out that at 0 degree Kelvin, it cannot carry current. The reason for that is, even though there are like this 10 power 22 electrons of the order of 10 power 22, they are all bonded to the lattice. They are not free to move, right? That's why at 0 degrees Kelvin, a semiconductor cannot carry current. Okay. Now what happens if I increase the temperature? I'll make it, let's say, room temperature. Okay. If you make it room temperature, essentially you're heating the material, right? Your material is now at a slightly higher temperature than 0 Kelvin. So when you do this process, you're supplying energy, and some of this energy is used in breaking the bonds. Okay, so breaking some of these covalent bonds, which are binding the electrons to the lattice side. So when you break this bond, the electron becomes free to move, and that electron goes into the conduction band. So when the electron goes into the conduction band, it can help in current conduction. So when you go to higher temperatures, you will have current conduction, which is possible. Right? So when electron goes into the conduction band, what happens to the valence band? Right? Because these atoms are electrically neutral. They are only sharing electrons, but electron is not being removed from the silicon atoms, right? So what happens if electron becomes free and then it's able to move around? Then of course it is going to leave a positive charge behind. Okay, and this positive charge, we are showing it as, we call it as a hole. Simply to say that there is a deficiency of an electron. A hole is simply lack of electron. So now the question is, okay, there is a hole in the valence band. Why do we say it is in the valence band? Because the hole is part of the lattice. It is the location of the physical location of the hole is basically where the bond was broken, right? So whenever we say conduction band, we say that it is the carriers anywhere in the lattice you want. But a hole is basically located to a specific region, okay? Not the interatomic distances, not those regions, but only in between two of the silicon atoms, right? So a hole is in valence band, right? That's the physical picture. Now, Can a hole conduct? I'm saying that the hole is captured, it's located at one between two atoms, right? Then will hole conduct electricity? You should think about it. Okay? You can pause a moment and think about it if you'd like. But it turns out that it can conduct electricity. You might think that it is fixed, so it cannot, but then it is actually conducting, because what can happen is there is nothing sacred about this particular location for a hole. You could always have an electron from the neighboring side, for example, here, can jump into this. Okay. When an electron jumps, the hole is filled up, but then a new hole is created at a different location. Okay. Then you can have one more electron jumping from somewhere else, and a new hole is created, right? So the original hole was filled up. I mean, in the sense, when you say hole is filled up, essentially the bond is satisfied, right? The valence requirement is satisfied. So there are two electrons shared between those two atoms. That's all. It's not a physical hole in the silicon. Okay. So now you are able to move this. The hole is actually able to move through the lattice. It is something similar to what happens in if you have a bubble of air in water. What happens? The bubble moves. It's not actually the bubble moving, but it is the water which is moving, right? The background, the water is moving, and because of that, the bubble appears to move. Similarly, even though when we say the motion of a hole, right, it is in fact electrons which are moving, but then it appears as if the vacant state is moving. Okay, so please remember this. Okay, so basically, whenever you say hole is in a valence band, it means that the bond, right? Basically there is a vacancy of electron at one of the lattice sites. Okay, that's a hole in valence band means. Okay. All right, good. So now because of that, what do we conclude? We conclude that electrons and holes both contribute to current conduction. If you have a metal, you would only think of electrons, but in semiconductors, you can have both this contributing to current conduction. All right. So now, how do we talked of electron going into the conduction band and leaving behind a hole in the valence band. So it appears that these things are forming in pairs. Okay. So we actually give them a name. We call it electron and hole pair, EHP. Okay. So electron and hole pairs, by this process at least, it is produced in pairs. Okay. So what are the various electron hole pair producing processes in semiconductors? One of them is heating. We already talked about it, right? When you heat a semiconductor, it produces electron hole pairs. And it turns out that the probability of generating, an electron hole pair by thermal process, probability of generating EHP by thermal process. Okay, this turns out to be dependent on exponential probability proportional to minus Eg by kT. Okay, so if you increase the temperature, you're essentially supplying more and more energy, right? So the fraction in the exponential reduces, and you get higher probability. Okay. So that's how at higher temperatures you're able to have more electron hole pairs. What happens if you have higher band gap? Well, band gap is the energy that has to be overcome to produce electron hole pairs, right? Unless you give that amount of energy to the electron, it cannot go into the conduction band. Okay. So that goes into the numerator. As band gap increases, the probability of electron hole pair generation reduces, right? So this is one of the processes, right? Thermal process. And the second process is basically optical absorption. Okay. When I say optical, I'm essentially referring to visible wavelengths. Okay. So what are the visible? Okay, by the way, I'm sorry, I didn't, this scale, you please make note, this is not your wave vector that we were talking about, but this is basically Boltzmann constant. Okay. Boltzmann constant. Sorry, I should have mentioned that. Okay. Anyway, yeah, coming back to optical absorption, we are talking about visible wavelengths. Okay. When we have visible wavelengths, what are the range? Visible wavelengths. It is basically 300 to 700 nanometers. I mean, you could even say 750 nanometers, but this is a broad range. All right. When you have a photon of this wavelength incident on a semiconductor, what happens? Okay. For that, we have to analyze what is the energy of a photon, right? So the energy of a photon is, we will like to, use it, we calculate, we use it frequently, so we will actually give you a simple formula to calculate. Okay. So we know that E is equal to h nu, that means E is equal to hc by lambda, and this can be computed, and we say that this is basically equal to 1.24 by lambda in micron. If you calculate this, you get basically E in EV directly. Okay. This is a simple formula that you should, I think, remember. It's very useful and it's very accurate for visible wavelengths. Okay. In fact, even others. Okay. So now, what is let's consider the green light, okay, which is the center of the visible range, we can say, right? Because it's 500 nanometers. 532 is one of the famous peaks of green, but let's take 500 nanometers. So if you have a 500 nanometer light or photon, what is its energy? It turns out it is basically 2.48 eV. Okay. So now let us say a 2.4 eV or 2.5 eV photon is incident on a semiconductor which has a band gap of, let's say, 1 eV. Okay. What happens? Well, the energy is higher, right? The photon supplies the energy to the electron in the valence band, and the electron makes a transition into the conduction band. Because there is sufficient energy in the photon to make this happen. And of course, you're never, I mean, traditionally, you're never going to put only one photon, you put lots of photons, so more electron hole pairs are generated. Okay. All right. So, what happens if you use, let us say, 1500 nanometer, okay? 1500, whatever, yeah, let's say 1550 nanometer, 1550 nanometer photon. Okay, this is a famous wavelength for telecommunications. Okay, all your optical fibers you use IR, near IR, which is basically telecommunications wavelength, we call it. Okay, what happens if you shine this photon? Will it, what is the energy? If you calculate, it turns out to be 0.8 eV. If you shine a photon of 0.8 eV on a piece of material which has a band gap of 1 eV, of course, it cannot produce electron hole pairs because its energy is not sufficient. The energy that supplying to the electron is not sufficient to make it go to the higher state. You might argue that, well, two photons can simultaneously contribute energy to one electron and then you can make the transition happen. Well, that is possible. It's called multi-photon absorption. But then the probability of that happening is very, very small. So we will neglect it, for purposes of this course. All right. So basically, the optical absorption process has been, we can summarize that, absorption, okay, whenever, when h nu is greater than Eg, okay, transmission when, sorry, we don't need to say this, so h nu is less than Eg, okay. Why do I say transmission? Let's say I take a thin piece of silicon, I shine this photon, okay. When the electron makes a transition from the conduction band into the from the valence band into the conduction band, then it is getting absorbed. The photon is destroyed. But if this transition doesn't happen, the electron stays in the valence band, then the photon can simply go through it. Okay? That's why we say that the photon gets transmitted. All right. So this is optical absorption process, one of the ways of creating electron hole pairs. So I listed a couple of more processes here, and those are basically impact ionization. Okay. When we say impact ionization, what we mean is, if you consider a piece of silicon, let's say, okay, and you apply a voltage, right? If you apply a voltage, what happens? Right? Assume that it's at room temperature. Then electrons will go towards the positive terminal, holes will go to the negative terminal. So the battery is causing the electrons to move and they acquire kinetic energy. Right? Kinetic energy is basically proportional to velocity, right? So now, as they move, if the kinetic energy is greater than Eg, what happens? Okay, if the electron has acquired a large enough kinetic energy that it is above Eg, the band gap. If that happens, electron can transfer, electron can transfer the energy to the lattice and cause a bond to break. Okay, this implies you have EHP generation. Right? Whenever bond breaks, you have EHP generation. By the way, yeah. So now, this is one of the processes. And when will it be significant? When you have large amounts of energy. If you put a large voltage, okay, then you have this huge amount of energy that is transferred to the electrons, from the external battery or whatever, and that leads to more and more broken bonds. You can think of it like a highway, and a car traveling on a highway. If the velocity of the car is, if the speed of the car is large, then if by chance when there is no damage, it's okay. When there is no accident, it's fine. But if by chance there is an accident, then the amount of damage it causes is proportional to its energy. Similarly, you can think of the electron as a moving car, and then it's actually colliding with the lattice, and there's a lot of damage to the lattice if the energy of the electron is large. So this process is known as impact ionization, because essentially you have an electron making a impact with the lattice site. Okay. Well, now I'm talking as if the electron is a particle, but we already saw that you could call it. I mean, you could also think of it like a wave, right? A electron has a probability, and then probability wave it travels. The same. I mean, it still holds. It's not. We are not negating that. You could either talk in terms of wave packets or electrons. Okay. All right. So this is one process, and you also have another process which is basically impact ionization. Sorry, high energy beams. Okay. If you have X-rays, these are high energy beams, right? Uh, if you have X-ray shining on a semiconductor, the energy of X-ray, the wavelength of X-ray is very, very small, 1 nanometer or so. Then X-ray energy will be very large. When the energy is large, it is going to cause electron hole pair generation. Okay, same process. I mean, like optical absorption, what happens, but it's actually even more higher energy. Okay, and this sort of impact with high energy beams is very significant in space. On Earth, the atmosphere protects all the high energy radiations. It blocks all of it, and so we are safe. But the moment you send a satellite into orbit, there's a lot of high energy radiation, and that causes a lot of electron hole pairs in the electronics in the satellites. So you have to do something special to make sure that the electronics still works. Okay, this is a branch of semiconductors that I'm sure ISRO and others are interested.